So in this section, we want to take a look at something called recursion or recursive definition. So start off with the definition. A recurrence relation for the sequence A0, A1, A2, etc. is an equation that relates A sub n to a certain number of its prior terms, where initial conditions A0 and A1 are explicitly given. So let's take a look at this sequence right here. So 4, 2, 1, 1/2, etc. And so when we ask ourselves what's the pattern, well, hopefully we can see that each term is half of the previous term. I start off with 4 and I half it and I get 2. If I take half of 2, I get 1. If I take half of 1, I get a half, etc. Okay, so here's the idea. I wish to construct a formula for A sub n and then compute A sub 10. So hopefully we can see that A sub n simply equals 1/2 A sub n minus 1, meaning the current term equals half of the previous term, with A sub 0, the first term, being 4. So A sub 10 is simply 1/2 of the previous term, which would be A sub 9. Well, and this is where the recursion comes into play. 1/2 of, well, what would A sub 9 be? That would be 1/2 of the previous term. That would be A sub 8. Okay, well, this would be 1/2 of 1/2 of, well, what is A sub 8? It is 1/2 of the previous term, A sub 7. And so hopefully we can see this pattern continue on downwards to where I get 1/2 to the 10th power times A sub 0. Well, this is simply 1/2 to the 10th power times 4. And if I crunch this out, I get 1 over 256. And so the 10th term in this sequence would be 1 over 256. Okay, let us continue with another example. Let's let A sub n equal A sub n minus 1 plus 2 times A sub n minus 2 for n bigger than or equal to 2, where A0 and A1 both equal 1. And then we wish to calculate A sub 5 recursively. Okay, so here's the formula or the definition of the sequence. So A sub n, that's the current term, equals the previous term, A sub n minus 1, plus 2 times the second previous term, A sub n minus 2. So the current term is equal to the term prior plus 2 times the term prior to that. So given some items, so A0 would equal 1, A1 would equal to 1. So A2 then is simply equal to the term prior, that's A1, plus 2 times the term prior to A1, which would be A0. Well, what is this? This is 1 plus 2 times 1, which is 3. Well, let's compute A3. A3, using this recursive definition, is equal to the prior term, A2, plus 2 times the term prior to that, that would be A1. So this would equal the term prior, A2, 3, plus 2 times a1. Well, what's a1? That's 1. And if we run this through, we get 5. Okay, what about a4? a4 is a3 plus 2a2. So this would be a3, that's 5, plus 2 times a2, that's 3. 5 plus 2 times 3, that is 11. Lastly, a5 equals a4 plus 2a3. That's 11 plus 2 times 5, so we get 21. So a sub 5 equals 21. Okay, let's do another recursion example. Okay, let's let a sub n equal 2n times a sub n minus 1 with a0 equaling 1. So first, let's write the first 5 terms of this recurrence relation. Okay, so we're told that a0 is 1. So what would a1 be? a1 would be 2 times the current index where I'm at, that's 1, times the term prior, a sub n minus 1, so that would be a0. So that's 2 times 1 times 1, that's 2. Okay, a2. This would be 2 times the current index where I'm at, that's 2, times the term prior, a1. Okay, so that's 2 times 2. a1 is 2, so 2 times 2 times 2, that is 8. a3, this would equal 2 times the current index, that's 3, times a sub n minus 1, the term prior, a sub 2. This is 2 times 3 times a sub 2 is 8. 2 times 3 times 8, that is 48. If I go a4, this would be 2 times 4 times a3. That's 2 times 4 times 48 to give 384. So this would be the first 1, 2, 3, 4, 5 terms in my relation. Now, we wish to solve this recurrence relation by iteration. So I'm going to scroll down and erase this right here so we can begin to solve this through iteration. So still looking at this same recursive definition, let's solve it by iteration. So if a sub n equals 2 times n times a sub n minus 1, then a sub n minus 1 would equal 2 times n minus 1. Notice whatever the index is, that goes right here, times the term prior. Well, that would be a sub n minus 2. Well, let's continue onwards. Then a sub n minus 2 would be 2 times the current index, n minus 2, times the term prior. That's a sub n minus 3. Okay, well, what would a sub n minus 3 be? That would be 2 times n minus 3 times the term prior. Well, what's the term prior? A sub n minus 4. So notice that a sub n is equal to 2n times a sub n minus 1, which then I can write as 2n times, well, a sub n minus 1, what is that guy? That's 2 times n minus 1 times a sub n minus 2. Well, what is a sub n minus 2? This is 2n times 2 times n minus 1 times what is a sub n minus 2? That's 2 times n minus 2 times a sub n minus 3. Now, let's see if we can't look at the pattern. If I continue this onwards, what do I have? I have each time, and all these are multiplied together, I have a 2, a 2, a 2. So it appears that I have a 2 to the n power. And then what are we doing right here? This is n times n minus 1 times n minus 2. If I continued it again, it would be n minus 3, etc. This is simply n factorial. If I take a number and multiply every successive number all the way down, and this is n factorial. So in general, a sub n equals 2 to the n times n factorial. So that's how we can solve a recurrence relation by iteration. Now, let's take a look at possibly the most famous sequence that can be described using recursive definition or a recurrence relation. So let's take a look. This sequence 0, 1, 1, 2, 3, 5, 8, 13, 21, etc. Let's look at this pattern. Okay, without much difficulty, hopefully you can see, if I take 0 plus 1, I get the next term 1. If I go 1 plus 1, I get the next term 2. 1 plus 2 is the next term 3. 2 plus 3 is the next term 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. So what's the pattern? Okay, each term is the sum of the two previous terms. So let's let a sub n be the nth term in the sequence, meaning a sub n is equal to a sub n minus 1 plus a sub n minus 2, where a0 is 0 and a1 is 1. So if I look at this, a0 is 0, a1 is 1, then a2 is a1 plus a0. Well, that's 1 plus 0, that's 1. That's this guy right here. a3, what's a3? Well, that's simply a2 plus a1. That's 1 plus 1, so 2. Well, what about a4? That's a3 plus a2. That's 2 plus 1, so 3. That's this 3 right there. What about a5? That's a4 plus a3. That's 3 plus 2, which is 5. There we have it right there. Okay? So it's important to see that the current term a sub n is simply the sum of the two prior terms, a sub n minus 1 plus a sub n minus 2. Now, this sequence is a very famous sequence, okay? And we call this the Fibonacci sequence, and it is defined recursively. So what we want to do next is we want to take a look at the ratios of two consecutive Fibonacci numbers. We want to take a look at the ratio of two consecutive Fibonacci numbers. So the Fibonacci sequence is as follows. So 0, 1, and now I simply add the two together. 0 plus 1 is 1, 1 plus 1 is 2, 3, 5, 8, 13, 21, etc. Okay? So let's look at ratios. Okay? Let's do A1 divided by A0. In essence, let's do A sub n divided by A sub n minus 1. So 1 divided by 0, we'll call this A1 divided by A0. A1 divided by A0. Yes, division by 0 is undefined, so we will simply write that down. Well, let's do A2 divided by A1. So that's 1 divided by 1, so 1. What about A3 over A2? That's 2 over 1. That's 2. What about A4 over A3? A4 over A3, that is 3 over 2, or 1.5. A5 over A4, that's 5 over 3. That's approximately, what, 3 goes into 5, 1.666, repeating. Next, A6 over A5, excuse me. That would be 8 over 5. A7 divided by A6, that would be what? 13 over 8. And so hopefully you can kind of see the pattern right here. So let's define B sub n as A sub n plus 1 divided by A sub n, or that's exactly what I'm saying right here. I've just got it off by a different index. It is defined to be the next term in the sequence divided by the current term in the sequence. Now, let's define rho. This symbol right here is the Greek letter rho. Let's define rho to be the limit as n goes to infinity of this ratio of b over n, b sub n, excuse me. Okay? So using some ideas from second semester calculus, and this is not a calculus course, so we're just going to use this fact, but it can be shown that the limit as n goes to infinity of b sub n equals 1 plus 1 over rho. So rho equals 1 plus 1 over rho. Now what I want to do is I want to solve this equation for rho. So here's the idea. Rho equals the limit as n goes to infinity of b sub n, which is equal to the limit as n goes to infinity of a sub n plus 1 over a sub n, where these a sub n's are terms in the Fibonacci sequence. Okay? So I wish to solve rho equals 1 plus 1 over rho. Okay, so let's do a little bit of algebra. If I were to multiply everything by rho, I would get rho squared equals, every term's getting multiplied by rho. I'm going to clear this fraction. Rho squared equals 1 times rho is rho, plus 1 over rho times rho is just 1. If I clean this up, that's rho squared minus rho minus 1 equals 0. And so what I can do is I can use the quadratic formula. So using quadratic formula from college algebra, I can then say that rho equals negative 1 plus or minus the square root of negative 1 squared minus 4 times 1 times negative 1 all over 2 times 1. So rho would equal 1 plus or minus square root 5 over 2. And if I select the positive root, and the reason I'm selecting the positive root is because when I was looking at all of these ratios, this a sub n plus 1 over a sub n, all of them were positive values. And so rho then equals 1 plus square root 5 over 2. Now this is what the number is exactly. I could approximate it. 1 plus root 5 over 2 if I wished. So 1 plus root 5 divided by 2. And I get 1.61803, etc. And so this is going to be an irrational number. The number is going to go on forever. It's not going to repeat. It's not going to terminate. But I could approximate it as approximately 1.618. Which is what we call in mathematics the golden ratio. This golden ratio appears several places, not only in mathematics, but also in biology and in nature. And so it's just a very interesting thing to see that as I take a look at this ratio and divide it out, I've already erased them, but I could go back and take a look at various ratios and see that as the ratios go towards infinity, they get closer and closer to this 1.618, etc. This 1 plus root 5 over 2, which we call the golden ratio. So that is recursive definition.